Welcome to this explainer. Today we are looking downward. We spend so much time looking up at the sun and the wind to solve our global energy needs, but beneath the Earth's crust lies a practically inexhaustible thermal battery. It's an unimaginable amount of power churning right beneath our feet, just waiting to be tapped, and it's been running continuously since the dawn of our solar system. So today we're going to explore the fascinating engineering and the complex geology behind exactly how we tap into the Earth's hidden fire to generate clean, continuous electricity. To truly grasp the scale of what we're dealing with, it really helps to look at the raw physics of our planet. Think about it like this. Earth is essentially a massive, continuously active pressure cooker. Beneath the relatively cool, thin crust that we live on, there's a vast mantle of semi-solid rock and a molten core where temperatures literally rival the surface of the sun. This immense thermal energy creates a powerful, constant outward flux of heat. It drives tectonic activity, fuels volcanoes, and creates the perfect geological conditions for massive energy transfer right under us. So what exactly is geothermal energy? Simply put, it's the power derived directly from this internal planetary heat. But the source of this heat is what's truly fascinating. It's a combination of two things. First, you've got the primordial thermal energy left over from the violent collisions that formed the Earth billions of years ago. But equally important is the continuous radioactive decay of specific isotopes, elements like uranium, thorium, and potassium, packed tightly inside the deep rocks of the mantle. It's basically a slow, continuous natural nuclear reaction, which ensures this ancient heat source remains virtually infinite. Okay, let's jump into Section 1, Earth's hidden heat and the geothermal gradient. The deeper you go, the hotter it gets. But scientists actually have a specific metric for this predictable rise called the geothermal gradient. On average, the temperature goes up roughly 25 to 30 degrees Celsius for every single kilometer you travel down into the Earth's crust. To put that into perspective, think about ultra-deep mining operations like the gold mines in South Africa that plunge miles underground. The rock walls at those depths are literally hot to the touch. The ambient temperature is so extreme down there that engineers have to pump massive amounts of refrigerated air into the shafts just to keep the miners from suffering heat stroke. That gradient is a powerful ambient force. Moving right along to Section 2, from deep heat to steam. Let's see what happens when water meets hot rocks. The magic really happens when this intense underground heat interacts with water. It starts simply enough. Rainwater or regular groundwater seeps down, percolating deeply through faults, cracks, and highly porous stone. Eventually, that water hits the intensely hot rocks of the geothermal gradient. Now, because of the immense weight of the millions of tons of solid rock above it, this subterranean water is under extraordinary pressure, and that pressure acts like a lid, allowing the water to be superheated well beyond its normal boiling point of 100 degrees Celsius without immediately turning into vapor. What we end up with is a highly pressurized, subterranean boiler room filled with a massive amount of stored thermal energy. So, how do we harvest it? Engineers drill deep production wells straight into these superheated zones. Once tapped, the highly pressurized hot water and steam violently rush up the well to the surface. We take that powerful rising steam and we use it to spin a massive turbine, which then drives a generator to produce electricity. It's a brilliant four-step process. What's crucial to understand here is that this is the exact same fundamental mechanism used in a traditional coal or nuclear power plant. Boiling water to make steam to spin a turbine is the backbone of the global power grid. The profound difference with geothermal? We don't need to burn any external fuel to create the steam. The Earth itself is the furnace. Which brings us to Section 3. The different types of geothermal power plants. Because geological conditions and underground temperatures vary wildly across the globe, engineers had to get creative. They've developed 3 distinct ways to process this heat at the surface. First, there's dry steam, which is the most straightforward. It uses natural, high-pressure steam venting straight from the ground to directly spin the turbine. Next is flash steam. Here, incredibly hot, highly pressurized water is pumped into a lower-pressure tank. That sudden, dramatic drop in pressure causes the water to instantaneously flash into usable steam. But we don't always get lucky enough to find those ultra-hot reservoirs. That's where the binary cycle comes in. This is a brilliant engineering workaround that takes lower-temperature geothermal water and uses it to heat a completely separate secondary fluid that has a much lower boiling point. That secondary fluid vaporizes, turning the turbine, which drastically expands the geographic areas where we can successfully build these plants. Now let's look at Section 4, the pros and cons. we need to weigh the benefits against the limits. When analyzing this technology, it's absolutely vital to look at the whole picture. On the advantages side, geothermal provides something grid operators value above almost anything else: baseload power. Unlike wind or solar, where you have intermittency issues when the wind dies down or the sun sets, geothermal provides steady, continuous electricity 24/7 with virtually zero carbon emissions. It completely solves the intermittency problem of renewables. However, it's not perfect. It requires specific geologically active regions, plus drilling miles into hard rock is incredibly expensive and capital-intensive upfront. There's also the very real challenge of induced seismicity. The process of extracting and re-injecting high-pressure fluids deep underground has in some instances triggered small-scale earthquakes, which means we need extremely careful monitoring and strict environmental management. Let's move to Section 5, Global Geothermal. Where is this actually happening around the world? Despite the geographical constraints we just talked about, several regions have fully embraced this natural engine and integrated it deeply into their power grids. Iceland is probably the most famous example. They sit directly on a mid-ocean ridge, allowing them to generate roughly 25 to 30% of their entire nation's electricity purely from geothermal sources. But here's a surprising fact. The United States is actually the world's largest overall producer of geothermal electricity by volume. This is largely driven by massive dedicated installations like the Geysers Complex in California. It just goes to show that this technology can absolutely scale to meet the demands of massive modern economies when the geology cooperates. To summarize our journey from the depths of the crust back up to our power lines, it all boils down to a beautifully simple progression. Earth's internal heat continuously warms the deep underground aquifers. That superheated water creates highly pressurized steam, and that steam turns the industrial turbines that ultimately generate our electricity. It's pretty profound when you think about it. This ancient, volatile geological process, literally the same process that moves continents and builds mountains, is being quietly harnessed to power our modern lives and light up our cities. The potential here is just staggering. Beneath your feet, the Earth is constantly producing heat. It's an ancient subterranean furnace radiating immense energy. And we've proven that we can turn that hidden fire into clean, continuous electricity. The core technology works, the primary fuel is absolutely free, and the source is virtually infinite on human timescales. So I want to leave you with this question. As deep drilling technology continues to advance, driving down costs and expanding access, what is stopping us from tapping into this hidden fire to power the entire globe?